In a standard neural network, a unit decides to activate through a strictly mathematical calculation. It compares a weighted numerical sum against a predetermined threshold, and if the total is high enough, it fires. This process relies on a scalar threshold, a simple numerical trigger, which requires a fixed, predefined topology. To process data, these networks must flow through layers engineered before the calculation even begins. Aurora moves away from the scalar trigger. Activation is instead decided by structural coherence. Structural coherence is the ability for two distinct pieces of data to successfully synthesize into a unified relationship within a given local context. Shifting to coherence-based activation changes how we define dimensions and layer boundaries, moving them from fixed constraints to variables determined by the data itself. The foundation of this system is a ternary vocabulary. States 0 and 1 act as defined complementary values, while the state of 2 operates as an open, pulsing receptor, a space of possible determinations actively susceptible to transformation. This ternary logic drives Aurora's core operator, the window. The relationship is defined by the equation W equals A, B, U0. A and B are the two input tensors being related. U0 is the space where the relation tries to build its output, starting as a tensor populated entirely by the state of 2. This operation follows the rule of dimensional invariance. The absolute size of the output matches the inputs, meaning U maintains the exact same bounding dimensions as A and B. Aurora builds hierarchical understanding through increasing geometric density. Because dimensions do not grow through concatenation, the network avoids the problem of increasingly long data lists. The window operator walks an ordered data cluster to find boundaries, isolating tensors T1 and T2. Forming the successful relationship achieves a coherent state, consolidating U into synthesized output TS. This tensor moves vertically, and the window steps forward to evaluate T3 and T4. Coherence is the mechanism for vertical hierarchy. It transforms a local relationship into a singular object that can participate in higher-level abstractions. The red section represents the incoherent window, where T1 and T2 fail to synthesize, being structurally incompatible in their context. Consequently, T1 ascends vertically alone. T2 shifts laterally to become the first input of the next window, testing a new relation with T3. This mechanism enables dynamic segmentation. The architecture discovers where one unit of data ends and another begins, without relying on pre-trained boundaries. The final routing state is the ambiguous window, shown in yellow. The output remains open, retaining its value of 2. Extracting structural data without enough context to close the relationship, the partially evolved tensor shifts horizontally, acting as a mathematical carry for the next window. This carry retains the structural data from the previous relationship, allowing it to test its configuration against new information found downstream. The ambiguous state provides Aurora with an operational memory. Rather than forcing an immediate calculation, the network can wait for context to resolve the relationship. We can see this emergent topology in motion by running a sequence of 5 tensors, labeled T1 through T5. First, tensors T1 and T2 interact. Lacking context, they produce an ambiguous carry. This carry tests against T3. Finding an incoherent relationship, the carry ascends vertically on its own. Left behind, T3 and T4 test coherently, fusing into a denser unit that ascends together. Finally, T5 reaches the end of the sequence with no remaining partners. It ascends vertically without modification. The resulting hierarchy emerged strictly from the internal relationships found within the data, rather than following a rigid human-designed layer structure. This process raises a critical question. What happens when the window hits the physical boundary of a sequence while holding an unresolved carry? Because no further context is available, into zeros or ones based on the limited context currently held. The window creates an elegant operational loop. Coherence drives synthesis, incoherence drives segmentation, ambiguity drives memory. By relying on coherence rather than scalar thresholds, Aurora allows the network to compute its own dynamic topology, organizing knowledge from the bottom up.